Welcome students to lesson 4.08 dealing with percent yield. In this lesson we will be looking at what the formula is, how we use the formula, and it is going to build on everything we've been learning throughout module 4. So be sure that you are understanding the material that we have covered in lessons 4.1 through 4.7. Before we get into that, let me just briefly mention what the objectives are going to be in this particular lesson. All right, for our Common Core standards, there are a few here that we're going to be looking at. If you would like to read through these on your own, feel free to pause the video and read through them. You can also find these in the course information section under standards. You can also locate them there and read them at your leisure. For this particular lesson, our main objective is right here, to calculate the percent yield in a reaction. Now, as I mentioned a moment ago, to be able to do this, there are some lessons that we need to have already mastered. Mainly lessons 4.6 and 4.7. In these lessons, we do stoichiometry calculations and we do limiting reactant calculations. Both of these are necessary to be able to successfully complete 4.08. So if you are still a little shaky with those lessons, please go back and review them. Watch the videos, attend an open tutoring session if you need to make sure you're understanding them well before you attempt 4.08. You also need 4.02, dealing with balancing equations. Again, we basically are taking everything that we've learned throughout Module 4 and we're going to use it as we do these percent yield problems. So again, if you're still struggling, we highly recommend that you do pause at this point and go back and go over those lessons to make sure you really have a good grasp on that material before you attempt 4.08. And again, we want you to have a successful experience with it. All right, so let's first talk about some real life examples of percents being used. Many of us, I'm sure, have gotten, graded papers back, and it's not always out of 100. So we always have to figure out, well, what letter grade do I have? Well, let's just say for an example, you get 63 out of 70. And of course, all of us know we simply take the 63, right, the points we earned, and then we divide it by the total points possible, which was the 75, and then to make it a percentage, we simply multiply it by 100%. So in this example, 63 divided by 75 times 100 equals 84%. So that tells us we got a B on that assignment. All right, well, really, when we do percent yield, we're doing a very similar type of calculation. We're taking what we actually get in the lab experiment, we're dividing it by what we theoretically should get in that experiment, and then multiplying it by 100%. We use percentages all the time. In the business world, we use percentages to talk about, how our company is growing or not growing. In sports, we use percentages to talk about if, a person's making, their free throws well or not. We use it all over the place. So there's lots of different real life examples where we use percentages. Well, chemists, just like other folks, like to use percentages. The reason we use percent yield is it helps us to determine, how well we're doing that particular reaction. Now, some stuff that you've already learned and already know, just a quick refresher here. In 4.6 through 4.7, we learned theoretical yield, limiting reactant, and stoichiometry. The theoretical yield, again, is the maximum amount of product that you can produce with the given amount of reactants that you have. The limiting reactant is the one that's always going to be used up first. In other words, it's the one that limits how much product you can actually produce. And then, of course, to figure all all of that out, we have to use stoichiometry. Remember, stoichiometry is the math of chemical equations. So we use our stoichiometry to first figure out the limiting reactant, and then that in turn also tells us the theoretical yield. It tells us how much we should be able to get if we did that reaction perfect. Now the actual yield is how much we actually get when we do the experiment. The stoichiometry and the balanced equation tell us how much we should get, and then we go and actually perform the experiment, and we find out how much we actually end up with. The actual amount is going to be less than the theoretical amount. And then the question may be, well, how can that happen? How could I have less than what I'm supposed to? Well, there's some different reasons for that. Let's just talk about those briefly. Some possible reasons that it'd be lower. Well, first off, conditions don't allow for the reaction to run to completion. What that means is that our reactants, for whatever reasons, do not completely 100% react with each other. So naturally, if they don't 100% react with each other, we're not going to have 100% of the possible product. The other thing is that the purification results in a loss of some of the product. In other words, the experiment itself. As you're going through the experimental steps, you may end up with some of the reactants being left behind. So that, of course, is also going to result in less than 100% yield. Now, the important thing, too, here to remember is that ideally we want to be as close to 100% as possible, because obviously the closer we are to 100, the better we're doing. But we're never actually going to get to 100 because of all the different conditions that surround that reaction that particular reaction we're performing. So we tend to call this efficiency. All right. In other words, how are we doing when we do that reaction? And if you are, like in private industry and you're working with chemicals, you want to know how well are we doing in this reaction. So the percent yield helps us get an idea of how well we are doing. And we simply take the percent just like we do other percentages. We take the actual, what we actually get, divide it by the theoretical, what we should be able to get, and then multiply it by 100 to make it a percentage. So it works the same exact way as it does for any other percentage. The hard part, if you will, is to figure out the actual and the theoretical. So let's look at how we would do that. Okay, the first thing we always got to do, anytime we do a stoichiometry problems, we always got to have our balanced equation. That's the first thing we have to do, write the balanced equation. Secondly, we need to take the information out of the word problem and identify the important parts that we have there. Thirdly, we solve for the theoretical yield using our stoichiometry. And then finally, you're going to take the actual and the theoretical and plug it into our formula and solve for the percent yield. All right, so let's look at an example. We got 9.80 grams of magnesium reacts with excess hydrochloric acid, and 29.8 grams of magnesium chloride are produced. What is the percent yield? Okay, well, first we've got our balanced equation, or not our balanced equation. We have our skeletal equation, Mg, magnesium, plus the HCl, hydrochloric acid. It's a single replacement reaction that we learned earlier in the module, where the Mg replaces the H, because Mg has a +2 charge when it makes a compound. We use our crisscross method, and the formula is MgCl2. Hydrogen is diatomic, so that's why it's H2. So to balance this, we would simply put our 2 in front of the HCl, and that would balance this equation for us. So we just put a 2 there in front of the HCl. Now as far as the information we need, we started with 9.8 grams of magnesium, so that's the Mg, with excess hydrochloric acid. Excess just means we have a lot of it. You can almost kind of think of it as I have an endless or abundant amount of hydrochloric acid. Therefore, it's not going to affect the final product. It's not the limiting reactant, it's the excess reactant. So in this case, the magnesium is a limiting reactant. So that's the one we're going to use in our stoichiometry to determine the theoretical yield. Okay, so again, first thing we had to do is write the balanced equation. And there we go, we have our balanced equation. Mg plus 2HCl yields MgCl2 plus H2. We already mentioned that we have 9.8 grams of magnesium metal. Excess hydrochloric acid means it's not the limiting reactant. And it produces 29.8 grams of magnesium chloride. So this would be our actual yield, because that's how much is actually produced when we did the experiment. So we're going to start with the 9.8, and we're going to use that to determine the theoretical yield. And the actual they gave us is 29.8. So how do we do that theoretical? Well, let's look at the next slide here. All right, well, we know the magnesium already is our limiting reactant. First step in stoichiometry, again, is to convert what you're given to moles. So we look up the molar mass of the magnesium. It is 24.305. We divide by it so that we cancel out the units. All right, so we have grams on bottom. That cancels out with the grams on top, leaving us with moles of Mg. Now if we go back to the balanced equation real quick, to get step 2, remember step 2 is the mole ratio. There we go. All right, so what we're looking for is the MgCl2. There's a 1 here in front of that. And we started with the Mg, and there's also a 1 in front of this. So that's our ratio, 1 to 1. Okay, so we have 1 mole of MgCl2 on top, 1 mole of Mg on bottom, and again by setting it up with the one we're looking for on top, the one we started with on bottom, we're going to cancel out the units. Okay, now the third step is we need the molar mass for the MgCl2. So again, we go to our periodic table. Magnesium is 24.305. Chlorine is 35.45 times 2, because it's MgCl2. And you add those together, and that's where this 95.21 comes from. Now this time we're going to multiply by that. That way we have the moles on bottom, and we have moles on bottom here, or on top, excuse me, and they cancel out. Now for the math, we just multiply by everything on top, divided by everything on the bottom. So it's 9.8 times 1 divided by 24.305 times 1 divided by 1. And of course we can kind of skip the ones because that's not going to change anything. Times 95.21 divided by 1. And we end up with 38.4 grams of MgCl2 for our theoretical yield. Now back in the problem, we were told that the actual yield was 29.8. So we simply take the 29.8 divided by 38.4, times it by 100 to make it a percentage, and we end up with 77.6% yield. Okay, so not too bad of a reaction, 77% yield. Certainly could be better, but it's definitely not horrible. We're not below 50, so that's not too bad. It says when 70 grams of MnO2 react with 128 grams of HCl, the reaction resulted in a 35.9 gram of chlorine gas. What is the percent yield of chlorine gas? Okay, so again, we are told that we are starting with 70 grams of MnO2 and 128 grams of HCl. So we have two reactants. Well, remember back in lesson 4.7, when you're given two reactants, there should be a light bulb going off in your mind saying, this is a limiting reactant problem. So that means we're going to have to take both of those reactants, figure out how much product is produced, and then from that we can determine which one's the limiting reactant, and in turn which one is our theoretical yield. And then compare that to the actual yield. And they tell us the actual yield here. The reaction resulted in 35.9 grams of chlorine gas. So that is our actual yield, 35.9 grams. Okay, so let's go ahead and start solving this out then. Again, our steps, we need to solve or write the balanced equation. We need to pull out the important information, which we just talked a little bit about. We need to figure out the theoretical yield, and then finally the percent yield. Okay, so here's the same problem again. First thing we need to do is balance. 1 Mn on the left, 1 on the right, the manganese. And that's balanced the way it is. Oxygen, we have 2 on the left. On the right, we only have 1. So to balance that, we need to put a 2 in front of the H2O. Okay, so now we have 2O, right? Because that distributes through. That also changes the hydrogen though. Now we've got 2 times 2, we got 4 hydrogen. So that means over here in front of HCl, we're going to need a 4. Okay, to give us our 4 H's. But again, that distributes to the chlorine. So we have 4 chlorines. Over on the left, we only have 2. So to fix that, we'd have to put a, or I'm sorry, we do have 4. We got 2 here in the NCl2, and then we got 2 over here in the chlorine gas. So total, 2 and 2, we've got 4 chlorines on the right side. So now we have our balanced equation. All right, so we start with 70 grams of MnO2 and 128 grams of HCl. And our actual yield, again, was 35.9. All right, so let's get going with our stoichiometry then. We're starting with 70 grams of the MnO2. All right, and our first conversion has got to be the molar mass. So we go to our periodic table. Manganese is 54.938, and we're going to add to that 2 oxygens. Well, 1 oxygen is 15.99, so we got to double that, and that gives us a molar mass of 86.918. that's per 1 mole of the MnO2. All right. Step 2 is our mole ratio. Well, for our mole ratio, we got to look at the balanced equation, right? Again, we are solving for Cl2. That's the one we're looking for. And we started with the MnO2. So the coefficients are 1 Cl2 to 1 MnO2. So we have a nice easy ratio here, just 1 mole of the Cl2 for every 1 mole of MnO2. Alright, and then that last step is the molar mass of the chlorine. So again, we go to our periodic table. Chlorine is 35.453, but it's diatomic, Cl2, so we have to multiply it by 2. And again, to cancel out the units, it's going to have to go on top this time. So up here we've got 70.91 grams of Cl2, and that's over 1 mole of Cl2. So multiply by everything on top and divide by everything on the bottom. Okay, and go ahead and pause your video and go ahead and calculate that out. All right, and you should end up with 57.1 grams of Cl2. Okay, now that may or may not be our theoretical yield. Now that may or may not be our theoretical yield. We have to then do this again. This time though we got 128.0 grams of HCl. Right, so again, the first step is the molar mass. So we take our periodic table, we look up the mass of H and the Cl, and since there's only one of each, we just add them together. And we get 36.461 grams of the HCl, and that's for every 1 mole of HCl. Step 2 is a mole ratio. Again, we got to look at the balanced equation. We're starting with chlorine, right? The one we're looking for. There's only a 1, again, in front of that. In front of the HCl, though, we've got a 4. So our ratio is going to be 1 to 4. So on top, we've got the 1 mole of the Cl2, and then on the bottom we got 4 moles of the HCl. Alright, so that's our mole ratio. And then the final step is the molar mass. Now, because we're going for the Cl2, it's going to be the same last step as it was in the first one. So 7.91 grams of Cl2 for 1 mole of Cl2. Okay, so 128 times 1 divided by 36.461 times 1 divided by 4, and then times 70.91 divided by 1. And that gives us 62.2 grams of Cl2. Sorry, that should be a 2. Okay? So, of the 2, the first one gives us 57.1 grams. The second one gives us 62.2. And remember, as we learned back in assignment 4.07, the smaller of the 2 will be the limiting reactant, because that's the one that's going to be used up first. So the 57.1 is our limiting reactant, which tells us then that this is also the theoretical yield. Okay, the theoretical yield. So now to get our percent yield, we're going to take the actual, which was 35.9 grams of the Cl2, and we're going to divide that by the 57.1 grams, and then of course multiply it by 100 to make it a percentage. And your final answer would be 62.9. All right. So 62.9% yield. Still, it's above 50, so it's not horrible, but definitely not, great, because again, we want it to be close to 100 for it to be really good. All right, so what's next? Well, if you haven't already done so, you do need to complete all parts of the lesson. That includes all the example and practice problems. Make sure you're clicking on all the hyperlinks to read up on all the information there. If you're still needing help, please attend our open tutoring sessions. There is also a review sheet in the Student Resource Center that you can use. And then the final thing you'll need to do is complete the 4.08 virtual lab, which is found in the Activities tab. If you need some help to complete that lab, you can always attend the completion sessions, and you need to check the schedule on your teacher's announcement page to see when 4.08 is offered next. Prior to attending the completion session, you do need to watch the video, so be sure you click on that link from your teacher's announcement page, watch that video, and do the things that are required to attend the session, and then come and join us there, and we can certainly help you complete that assignment and submit that to your teacher. And then that, of course, is the final step, is to submit that lab report. Once you're done with 4.08, you will then be ready for your Module 4 discussion-based assessment, which is your last discussion-based assessment for the first semester. And then you just will have an exam and your segment exam. So you're almost finished with first semester. So we hope this was a great experience for you, and we look forward to talking with you soon.